Hello, everyone. Welcome to the first talk in a new seminar series called Distinguished Seminars in Optimization and Data. I just wanted to tell you a couple of words about this series. This is a joint interdepartmental seminar series that we have just started. It is supported by several entities. I want to acknowledge them. One is IFDS, that's the NSF-funded Institute for Foundations of Data Science, many of you are familiar with. PIMS, Pacific Institute of Mathematical Sciences, is also one of the supporters. Plus, additional funding came from different departments on campus who have all pitched in to make this happen. The Computer Science and Engineering Department, ECE Department, Math, Applied Math, and Statistics departments all have participated. So the goal is to bring to campus speakers that can provide talks of broad interest to audiences that touch upon all these different fields. And today we are very proud to have the first speaker. And I would like to invite Professor Rekha Thomas to introduce our speaker. Thank you.
Thanks, Mariam, and thanks everyone for coming and finding the room. It's a great pleasure to introduce Eva. Eva Tadosh is the Jacob Gould Schurman Professor of Computer Science and the chair for the second time at Cornell University. Her degrees are from Hungary. Both her undergraduate and her PhD degrees are from Hungary. She has a huge number of awards and honors that you probably saw in the bio, and I won't read out all of them, but she's a member of the National Academy of Engineering, National Academy of Sciences, the Hungarian Academy of Sciences, the American Academy of Arts and Sciences, and has won a number of prizes, the Gödel Prize, the Danzig Prize, the Packard Fellowship, Fulkerson Prize, the von Neumann Prize, medal, and so on. There's a longer list you can read. She is a world expert on algorithms, algorithm design, game theory, and so on. So she will be speaking to us today about stability and learning in queuing systems. For me personally, this is a very special event. When I was a graduate student at Cornell, Eva was a young professor in the same department in operations research. She was the only woman, which was already very inspiring. But much more importantly, she was this young woman who was this amazing superstar. So it was just a very inspiring thing to have Eva in the department. So especially happy to have her here. Thank you.
Thank you. Thank you so much. It's very appreciated, and it's great to be in person, and great to see so many of you in person. That's really cool to have a large audience. I probably should start by apologizing with every single one of you, because as I understand it, or even as I see the people I recognize, is that it's a mixed audience from people who are not experts in theory of computer science and game theory, and people who are. So probably I will do a horrible job of losing people who are far enough and not offering enough detail for those who are close enough, and I apologize. I'll try my best. I think the best you can do is actually raise your hand and ask questions, and hopefully that will somehow help me cater to all of you who are around, and I'll try my best. I'm also happy to talk to any of you afterwards with, especially those who want more details, but if you have questions, it's always good to ask early on. And thank you for the generous introduction, and I don't know, it's always awkward to listen to one's own words. And I guess from this perspective, I always viewed myself as somewhere between multiple communities. So for the last 20-somewhat years, I have been in computer science, and I'm chair for computer science for the second time. But indeed, my roots are actually in mathematics. Like my PhD was mathematics, and in Hungary, I was part of the maths community. So I like the theme of this series, which connects these different communities. So that's cool. So what I want to tell you about is something about game theory and repeated games, and in particular in a queuing system as an excuse for this. But let me actually start with sort of the bigger piece of, and it's joint work with Jason Gayatonda. Jason is a graduating student looking for a postdoc, and maybe I shouldn't say this, but Cheyenne generously offered him a postdoc. So there is a chance that he actually will show up here. I think it's his first offer, and he's very happy with it, and it's a high-ranked position on his list. So he might show up here. He's a great guy. Okay, so where's the sort of bigger distance where I'm coming from is I've been interested in learning in games and in people interacting in multiple setups. And I guess the theme that I have most interested in or did most with is what's called price of energy, sort of understanding of how much selfish behavior of the agent hurts the social welfare. So how much does it make life worse that we're not coordinating between these guys, but they all making selfish individual decisions. That's called the price of energy, and that's sort of a interesting line of research. Many of the game, like classical, the beginning of this line of work was looking at Nash equilibrium as a stable solution of an outcome, and asking this question in a stable outcome. And then one sort of line of work that became very successful and prominent is say, wait. Many of the games in life are repeated, like we regularly interact. And I guess in these regularly interacting games, often there isn't that people do insane amount of previous work to figure out what is the Nash equilibrium, but they just start participating and hopefully sooner or later figure out what the right thing to do. And these are usually the kind of games that both are repeated like lots and lots of times. And second of all, the individual interaction don't have much value to them. It's the volume of interaction that causes it to be valuable. And the dominant example of this is not actually what I'm going to talk about, but instead advertising auction. If you think about what happens on Google or whatever web page you might be looking at with advertiser, what the advertisers pay for putting the ad up is fractions of pennies. The expensive ones may be a bit more than that, but it's really not much money. But it's a $1 million industry. That's what many of these companies, Google including, lives on. So what does that mean? It's a game where the overall value of the game is insanely big, but the individual interaction is not. These kind of games are apt for using the game to learn how to behave. Like the individual interaction is so cheap that doing lots of pre-work and spending millions of dollars to figure out how to bid, that sounds a bit crazy. You can just use the game itself to learn how to bid. And that's what's getting molded in what's sort of learning in repeated games, where I can ask a lot of good questions, and some of which I will offer you some answers to, and some of which I will not. That is, we'll end again with saying that these are the nice open questions. I should ask, what do I mean by learning? I'm definitely going to ask what kind of guarantees can offer for the outcome when they learn. And these are the sort of questions I'm trying to ask. If I go back to classical work, then the example that I worked a lot of and I still love as an example is traffic routing, that is cars or packets on the internet, getting from point to point. The simple version of it is a congestion game, which I guess the rules here were that you just measure how long it takes to get across, and that the assumption is that the bigger the congestion, the slower it is. Like, it's a, on the nice models here, there is a function that maps the congestion on an edge to amount of time it takes to get across from the edge. It's a simple and elegant model. And in this model, something that I guess more than 20 years ago, we proved with Tim Ravgarden that the Nash equilibrium is not so horrible. And this is the definition of the not so horrible we proved. That is that the cost or the total time it takes in a Nash equilibrium is no worse than the centrally optimized solution with double the traffic rate. So this is going to be sort of the model I want to go to. Now, classically, this is what price of energy is. That is measuring the cost of Nash equilibrium compared to a socially designed cost. And from this perspective, you can look at that theorem up there and say that, well, yeah, that over there is called a cheat. Why am I cheating? Because I'm comparing the cost of Nash equilibrium to something with double the traffic rate, which you can call a bi-criteria optimization or a cheat, your choice. But instead, I'm going to want to call it this. I want to ask you, how much extra resources do I have to give to the system so that the performance is reasonably okay? And I guess I'm claiming here that enough capacity to accommodate double the traffic rate is the message here. That if you have enough capacity in the routing system to accommodate double the traffic rate, then a Nash equilibrium has a good solution. That's sort of the message. Again, this is not the model we're going to talk about, but I really like this message in a way better than that message because it's a more actionable message. It asks you, what should you do to your system so that you have okay performance? So we can also say that just the dual optimization problem, I'm optimizing something else. Okay, the concrete model I'm going to talk about is not actually traffic routing, but a very, again, super simplified model of packet routing, not thinking about cars at all, but back to packets, and actually a super simple version, but modeling a different aspect of packet routing. When there's too much congestion in the internet, then packets get dropped. That is not happening to cars. We do not drop cars, but we do drop packets. And what happens when you drop a packet? It gets resent. So that makes the game a little bit different because what happens is as you repeat the game, that is I have these packets, and then there's this old packet that got dropped that has to get sent again. So there is going to be a carryover effect between iterations, namely drop packets need to get sent again. And that is a feature that I want to model. I'll make this more concrete and very simple in a second. I want to admit another part of what I want to simplify in life. I know that actual life is complicated and you might be sending packets and different moments in life. But I'm going to think of a very coordinated, simple version of repeated game. There is iteration 1, 2, 3, 4, 5, 6, and named after various numbers. And every iteration, you do something and some outcome happens. But what that means is that there is a coordination between iterations. There is not sort of a random times you wake up and do something, but instead there is time 1, time 2, time 3. It's a simpler version of life. Again, a simplifying assumption. The condition that I will want the learners to satisfy, and I'll come back to this about 10 times in the talk, is something that is, if you're scene learning or use learning, is a learning condition that all the game theorists love, including me, or used to love, including me. It's called the no regret condition. And I guess I wrote it out with utilities, so assuming something positive happens to you, you get money, or you get home in time, or whatever, some positive thing happens in your life, then the requirement is that you repeat this time over and over again. And so this here is the utility player I got at time t. So at is a vector of all the things actions that different people take. So this is an action vector. It's a game, so your utility depends on what everyone else did. And this utility is summed over time t is what you got over a long period of time. But I'm hoping that you do at least as well as any single action with hindsight. So for example, if I think of packet routing and a path you choose for your packet to send on, then if there is a path that consistently every single period is pretty damn good, overall it always gets you home in time or whatever the objective function is, then please notice this, and you don't have to use it, but at least do it as well as that one. So this is, I want to view it as actually a low benchmark. You can do better than this. Going back to the driving example, you could realize, and I don't know the highway numbers around here, I apologize, but you can realize that driving home on this highway on the rain is really bad because it gets slippery and traffic gets bad in the rain. So when it rains, you're supposed to drive that way. When it doesn't rain, you drive this way. So you're doing better than any single option with hindsight. But if there is a really good option, either do it or do something better than it. What's nice about this condition is two things, and I'll come back to this also. One is actually algorithmically doable. There are plenty simple algorithms that achieve this condition. And second, it does sound humanly believable that people should be able to do this well. Like it's not, doesn't feel like a very undoable condition, even for humans. I don't have it on the slides, and I can spend more time, especially if anyone asks, but there is both sort of data experiments with Microsoft data and human subject experiments with lab human subject trials. People tend to satisfy this. This is not an undoable condition. So, and of course, it's nicely mathsly expressed. So someone with a maths PhD like myself, it's a maths condition. It's very usable. One thing I didn't emphasize here is a little O of t here. Of course, this is a learning assumption. So in the first couple iterations, who knows what bad things you do till you learn. So this is over a capital T amount of time. There's a little bit of error. But the error should not go linearly with time. Like you should just, upfront you're making mistakes. Yeah?
Could you explain the notation of A subscript minus I?
Oh, yeah, good point. Thank you. So A is a vector. So this was the vector of what everyone else did. And what this is trying to say here, what would have happened if you consistently did this single action x? That is, A minus IT is what everyone else did at time t. And x is the possible other action. So in the driving example, everyone drives the way they did. You change your route. And how does that, what would have happened? Every morning after you went to work, you open the radio or open the map and realize that had I driven that way, it would have been so much faster. You add up those numbers. But again, it could be that, on even days you should drive left and odd days drive right. That's very hard. I don't know. But if there's a single good solution, an x that's consistently good, or at least on average good, then I ask you to do at least as well as that. That makes sense? Thank you for asking. And again, I very much want to encourage everyone else to ask. So what was right and why we all love this condition is the following set of results, which is maybe the precursor of what I'm going to talk about. So price of energy was originally defined by Koutsoupis and Papadimitriou in a paper in '99, so now more than 20 years ago. And indeed, they talked about Nash equilibrium only. So the ratio of how much utility people get at a Nash equilibrium, where A is a Nash equilibrium, compared to some socially defined optimum. And then 10 years later, in a sequence of papers starting with a bunch of people working with Avrum Blom and then really summarizing by a beautiful paper of Tim Ravgarden, said that, wait, we don't actually need to assume that we get a Nash equilibrium. It's enough to assume that everyone is a no-regret learner. So you get exactly the same band. Whatever happened over there happens over here too. If we're making the assumption that that it's a repeated game and all the players doing no-regret learning. Doesn't matter what they do. They can all run different algorithms. As long as they satisfy that no-regret condition, we're all home. Which sounded cool. And Liv and I worked on this. And we had some more results saying that, we can even keep changing the game underneath the people or keep changing the population. It's all OK as long as everyone learns enough. There are all kinds of extensions. So we thought that the message is no-regret is natural. It's strong enough assumption that everything works beautifully. And that's what we need to have. There was one handicap, which I a little bit hinted at in the beginning, and that's what this talk was motivated by and is about, is that the assumption on the set of results is that a clear state new copy of the game, that there is no carryover effect, that whatever happened with iteration 1, iteration 2 is a whole new copy. And the only thing that you carry over is your memory of what you learned. Like you're learning, it's an all new copy. And the question is this reasonable? And I guess my answer is sometimes yes, sometimes no. So in the traffic routing construct, it's, of course, if you're talking about morning rush hour, it's reasonable. Like no matter how bad Monday morning traffic is, by Tuesday morning, those cars went home. Like somehow it got solved. It might have been bad, but they're not sitting on the highway Tuesday morning. But if you change the time scale and say do second or millisecond by millisecond packet traffic, then it's not true. Whatever is happening at millisecond 1800, 1801, the same packets. They're still there. They're still causing trouble. And again, it's not as much a difference between cars and packets, a difference between the time scale. If the time scale is big enough, it's OK. If the time scale is not big enough, it's not OK. So there are a bunch of these, and I guess I started with mentioning ad auctions. That's also a system with carryover effect. But packet routing is one of them, where there is carryover effect between the iterations. And I think we should ask the very same questions for these games. In fact, I claim that most of the games we do play repeatedly have such carryover effect. It's not an anomaly, it's the rule. And therefore, those results have a limited validity, and we should think about what happens if there is carryover effect. And we should ask the same questions, the one I love, and I said I will ask in the beginning, how much more capacity does the system need to survive in a repeated setup despite the carryover effect? I should ask also, how good is no-regret learning, and should we, both in, if they do no-regret learning, good enough things happen, yes or no, and is there a better format of learning than no-regret learning? OK, so this was the sort of where my motivation is coming from, and I'm very happy to talk to any of you about other applications of this. As I said, most repeated games in life have this property that there is carryover effect. So I think there are many interesting questions here. The concrete result I'm going to tell you about is in a packet routing, in a very simplified packet routing model. And here is our super simplified model. There are a bunch of queues that will get packets at a Bernoulli process with rate lambda I each. So with every iteration, again, time comes in steps. Every step t, with probability lambda I, a new packet shows up in that queue. When probability 1 minus lambda I, nothing showed up. I have a bunch of servers here. And the servers, probably I shouldn't even have this, but I do have a probability mu j that they successfully serve a packet. If you don't like this, probability 1. It's really to have support induction proofs. I like the probabilities there, but it's not important for the result. Each time step, each queue can send one packet to one server. So this is modeling packets in the routers in the internet. Indeed, they only have one head, and they can send one thing up there. And then, of course, not too surprisingly, every server can only serve one of the packets. Here, I'm definitely cheating. So anyone with a more systems-ish background, it's better if I admit it right this very second. I know that servers or routers in the internet have a small buffer, and they only start deleting, rejecting things after the buffer is full. Our results actually don't have buffer, and it's an interesting question. If I add a little bit of buffer, how much things will change? At the moment, I'm dropping everything right away. So there's no buffers here. So the system is everyone sends it there. If it didn't, if sometimes works out and that gets sent forward, and what doesn't work out instantly sent back and got rejected. And I guess one thing you should ask me now, or very natural to ask me, when this conflict happens, how do I choose which packet to deal and which one not to? And I'm, again, happy to answer what different rules would do to the system. The rule that works nicest is if I favor the older packets, because that helps things get through. If you've been in the system, we really need to get you through. So that's the system I'm going to analyze. The routers make an effort to try to serve the oldest packet. The packets carry a timestamp, and they try to make an effort to carry the oldest timestamp. So this is the system I'm using. And again, if there are questions of what exactly is happening here, then it's a good time to ask.
So
any queue can send to any server. As I will admit in 2 slides down from here, there is a nice extension to what we do by a couple of people, including Hu Fu, who is yet another Cornell graduate. at UBC, thank you, that just appeared at the Vine conference months ago that extends it to not even just bipartite graph, but generally all networks. So while we somehow, our work is limited to this everyone can send everywhere, that's not, it turned out not as essential as we thought. What I'm going to start with is give you a baseline measure. That is, I need to know what the optimum is. How much capacity do I actually need had I coordinated? And then tell you what we can do if there's a game here. So let's start with the baseline measure. So what would be the baseline measure? I guess a baseline measure, I should ask, okay, what makes this doable if I'm allowed to coordinate? If I'm allowed to coordinate, I will never send 2 packets to the same place. That would be crazy of me. I will just figure out centrally of what's best to serve there, and I send that. So how would I coordinate? First of all, just as a natural sort of math assumption, because this is all about the optimization version anyhow, let's order both the packets and the queues so that they quality order. And I claim that there's the following condition is both necessary and hopefully very believable for you that it's sufficient. But the necessary, I will convince you. This is the condition. So let's actually, this is many conditions. For every k, there is a condition. Let's start with k equals 1. So k equals 1, the condition is that the queue that gets the most packets has a server that's capable of dealing with him. Like, if that's not the case, then this poor queue that has a lot of packets is stuck because the probability that his packets get served is lower than the probability gets a service no matter where hell he sends his packet, even alone. So even if there's nothing else here, just that top guy, there's no way he can survive. Yeah, he needs some place where the service rate is good enough for him. Similarly, if I take the top 2 queues, because everyone can only send to one place at a time, there must be 2 servers that are capable of dealing with these 2 guys. So the assumption is for every k, if I take the top k queues, the amount of service they get, some packets they get is less than the service rate of the top k servers. This is very, very hopefully apparent that this is necessary. And it's maybe not that hard to see that it's actually sufficient. So this is a stochastic domination condition, that kind of condition. And using sort of basic stochastic domination theory, you can decompose it into matchings and always use those matchings. It's not that hard to prove that this is sufficient if you were to coordinate. But in any case, it's obviously necessary. And why is this nice? Because, and again, I'm kind of sloppy about the strict inequality, but if you're a queuing theorist, you know that we actually need the strict inequality, but don't worry about so much whether it's strict or unstrict. Why is it nice? Because, again, it's a very simple mathematical condition. And when I say I want to give how much more capacity do I need to give the servers, what I'm really asking, if I want to put here a multiplier here, what multiplier is necessary here to make it OK despite the selfish behavior of the servers? That's basically what I'm asking. So is it, if I put here a factor here, like I make half. Half would mean that the capacity is twice what I need centrally. And this is what our theorems are saying. So theorem 1 is that factor of 2 if everyone is a learner. And this is what Hufu and a bunch of other people in current Vine extended to networks. So everyone's doing no regret learning. Then factor of 2 is what? Necessary and sufficient. So it's a tight bond. And I will give you a short sort of outline of why this is true, so at least limited to our settings. What I also want to convince you as part of this talk is that this is not the end of the story. Even though this band is tight, it seems like no-regret learning is not quite the right learning method here. And here is an alternate theorem that I will use to convince you of this. And what the alternate theorem says, at least maybe a bit cryptically right this very second, that if something is wrong up there and no-regret learners are not patient enough to understand what they're doing, And if we look at a better way of evaluating what they do, then you don't need a factor of 2. This little bit smaller, whatever, bigger factor is enough. So, you know, E over E minus 1 is, that number is E minus 1 over E. So a bit less is enough. This is an equilibrium analysis, this lower one, whereas that one is a learning outcome analysis, and I don't have a learning outcome, or we don't have a learning outcome analog of this. I can't do this with learning. I wish I could. Like, I don't have a learning algorithm that achieves this. What I'm going to do as the outline of the talk is I will try to give you a summary of why theorem 1 is true. I hopefully, with enough detail, it's a talk, and maybe I spend too much time on other things, but it's not giving you a glory detail every detail part. But I think I can give you a sense of why is it true, and why do I need a factor of 2 there, which hopefully is some amount of insight. I will not actually prove the second theorem at all, but show you an example that actually drives home of what's wrong with the no-regret condition. Just to give you some sense of the theorem, the second theorem, it's easy to show you what the worst case example is there. So where the E minus 1 over E is coming from, so I can't stop myself from showing that. But the proof is, you know, 2 proofs don't fit in a single talk, and I know, it's a decision. And then I'll try to tell you a little bit of what I'm interested in for further research. So that's the plan here. Again, good moment to ask question. Again, what's coming is a bit of an outline of why is no regret good for anything, and why is factor of 2 capacity bump up is both necessary and useful for proving something good. So it's a you know, there's a super powerful technique here that I neither invented nor was the first to use. It's a potential function method of Pimentel and Rosenthal from 2004. Has been used in the CS community already multiple times. And what this is a pure probability statement. Here's what the probability statement says. If you have a function, whatever you name the function, which I didn't name over there, I'm going to name it phi. If I have a function phi that evolves step by step and has the following property. When this function phi is really big above some bound, then in expectation, it decreases. It tends, when it's big, it tends to come down. And so that is negative drift when large, and sufficiently regular, which just means it doesn't jump up and down like crazy, like the second moments or something are bounded. That's what it means. Then this function expectation remains bounded. This is very believable, but it's a hard mathematical theorem. Okay, again, what the theorem says, a function that can go upwards when it's low, but when it's very high, it tends to come down, or in expectation, it comes down. And it doesn't jump like crazy. Then the expectation stays bounded over time. So that's the theorem we want to use. I will actually use it on a funny potential function that I will convince you is an interesting function, which is actually the square root of what I called phi. So phi starts with phi tau. Tau is a time step. And phi tau is the number of packets in the system that are tau time or older. And phi is, of course, the sum of all the phi tau. So for example, a packet that are 100 steps old is contributing 100 to this, because it contributes to phi tau for every tau that's less than 100. So that, you know, every packet of ht contributes t to this. So I added up all this. I'll convince you in a second that square root might be not crazy. But first I want to convince you that this is not a bad function, in the sense that if I can use that theorem, if I can say that indeed this function will remain bounded in expectation, then the Q stayed bounded. Because, you know, a Q that got infinitely long or very long, there must have some old packets in there, like every step only one packet could have come, so there must have old packets. And old packets push up this function. So if this function stayed bounded, my Q stayed bounded. So that's a good way to go. And then I'm claiming that the factor of 2 slack is necessary and useful for the negative drift. So only thing I'm going to convince you is that the negative drift, which was the most important condition here, that when large it has a negative drift, that the factor of 2 bump up is kind of seem like it's necessary there, but definitely very useful. So why am I what am I hoping to tell you about this? Well, I want to focus on not actually all the packets that are old, but a particular time cutoff, like tau, and look at all the packets in the system that are tau old or older. Now, what's special about these packets? That I favor older packets. So whenever any one of these guys sends to a server, one of them will get served. So as far as this group concerned, the other packets don't even exist. Like, they have priority over everything. So they're kind of alone in the system. So I look at a long enough period so the no-regret band counts. Remember, no-regret is a learning band. Initially, they can make errors, so I need a time step to make sure that the no-regret has byte in it. And I look at that and say there are 2 cases. Case number 1, the queues that had these old packets actually knew what to do, and they went to the best servers. If that happened, then they got server ample, actually better than that. And I don't even have to say they fully went there. They went there enough to occupy at least half the time, kept these things busy, because I have a factor of 2 bump ups. So one case is they went there well enough, at least half the time, half the time steps ahead, these things were occupied, and then one of them got served, and we had enough service capacity, and life was good. Case 1. Case 2, obviously, will be that's not the case. That is, I see. Then the function went down a lot because all these packets got served, and function went down. Case 2 is the opposite. They didn't manage to occupy the good servers half the time. Wait, they're good servers. Half the time they're empty. They could have gone there. They had priority. The no-regret condition will kick in. They had a place to go, and they didn't go. So no-regret tells them they must have gotten this much good service someplace else. Why do I need the factor of 2? Because I either need that either it's well enough occupied, or it's well enough empty. And that's exactly the factor of 2. Either half occupied, or it's half empty. So this really needs this argument needs the factor of 2, and in fact, we have an example matching it, that indeed you need the factor of 2 here. And by the way, you need it, as in you can run your favorite no-regret algorithm, and it needs a factor. Like, it doesn't work without the factor of 2. OK, and then instead of focusing on a single cut of tau, I just do it for all taus and add them up. And that's where the argument's coming from. Now, I do admit, especially with anyone who is more of a probability background, which some of you definitely are, that there are some details I'm sweeping under the rug here, and I can unsweep it or at least summarize some of the details. One of the details is that this is an infinite process, and expectations are a little iffy to work with, because under infinite time, bad things will happen. So actually, we're using a high probability band for the learning, rather like assuming that you learn with high probability rather than with expectation, which does make it easier. But maybe a bigger problem is that I cheated you with the potential function. As it turns out, the potential function I gave you does not have bounded moments. And it doesn't have bounded moments in the weird direction that if I understood the maths better behind that theorem, I don't understand why they need it. This potential function cannot jump up, but it can jump down. There are some weird cases where somehow a queue got a packet and was very, very old and added really to the potential function. And you're very unlucky, but no, there's a huge gap, and there are no packets there. And as soon as this guy left, the potential function went down like crazy. So it can actually jump down. But the theorem needs bounded moments in both direction. So we have to change in a way that maybe every probabilist would expect me to want to change. Instead of working with the objective function I gave you, I work with a deferred decision model. So instead of thinking about how many packets are in the system, I just look at the oldest packet in every queue and take the expectation of the rest. It's not, it is sort of pretty simple maths. And this is what the true objective function we work with. So if tau it is the time step on the oldest packet on qi, then that expression I wrote, lambda times ti minus tau, is the expected number of tau or older packets he's supposed to have. And this objective function has bounded moments, and it's the expectation of the other thing. It's roughly the same thing. So this one works. One nice thing that may be good to come to, that if I actually add this up over all times, I roughly speaking, the quadratic objective function where you make you feel comfortable about square root, that's the 2 norm of this function that we're using, which I think is unnatural from its own perspective. But we actually came from the intuition I used in the explanation rather than the 2 norm. But it's nice to come up with, realize that what you're doing is the 2 norm really, which is a natural objective function anyhow. Yeah?
Do you need a factor of 2 at every server, or do you just need a factor of 2 at, like, the servers with the most capacity or something?
So I think I need a factor of 2, and I'm paging back to that slide. I need a factor of 2 on this condition. So, but I don't know, certainly our theorem needs it, that if for all k, the top k server, top k queues should only have half as much demand as the top k servers. I can certainly create, for any fixed k, I can adopt my bad example to that we need it right there.
And do you have a sense
I
of,
think,
like...
I need to think about this.
Okay.
I think yes. Certainly, if I'm allowed to put a bipartite graph, then I will need it. But okay, good question. I need to think about, is there a weaker version of this theorem? Sorry. But definitely, we need it. What I promised to do is actually, what I did give you some hint of this factor of 2 band. What I promised to do next is tell you that this isn't as good as it gets, and there should be a better results out there. And here is the hint of the better. So this is, again, the claim. At some equilibrium of a game that I might not fully define even in this talk, you don't need a factor of 2. A smaller factor is enough. Cheyenne, you have a question?
You need a square root for the moments?
Yeah, for the moment.
Without it, it's not bounded?
Oh, good question. Yeah, without it, it's not bounded. Right? It's a quadratic function. If you increase it by 1, then the square could increase very highly, whereas the square root cannot. I think yes. In fact, I think I need it so much that then even, I have this bad feeling that in that theorem, you only need the bounded moments on the upper direction, not in the lower direction, even though the theorem doesn't say so. But this one, I think, will become bad in the upper direction.
That's the original theorem for non-negative functions? Or?
Yeah, for non-negative functions. OK, so here's the example that I want to use to convince you that there is something interesting here that goes beyond no-regret learning, and no-regret learning is too myopic. And this is sort of the last technical thing I want to show you. It's a super simple example. 2 servers, 2 queues. The 2 servers have arrival rate just above 50%, so 0.51. So, a little bit more than a half. And there is a perfectly good server that always serves, and a pretty not so good server, well, less than 50%. Numbers don't matter. Less than 50% is what matters. First of all, let's agree that there is not a factor of 2 blow up here. So this is not good. According to our theorem, it's not enough capacity. And in fact, it is not. If they both of the queues send it to the upper server, then you're not surprised to hear that they get 50% service rate there, right? I mean, they share it 50-50, which is not as big as 51. So first of all, the queues will grow linearly because 51 plus 51 is more than 1. And second of all, they will have no regret. Now, why do they have no regret? Is because if they were to deviate, Up there, they're getting 50% rate. Here, they're getting 44.7. That's less than 50. They have regret. It's a bad idea to use this lower one. Make sense? Except for it's not true. Moving to that lower server, say a little bit, 10% of the time, is actually good. And I don't mean, you might think that it's altruistically good. That is, it helps the other guy, because 10% of the time he's alone. I mean, it's selfishly good. Why is it selfishly good? Because, for one, if this fellow 10% of the time already clears it, there will be time steps he has nothing to send. So it turns out I will be alone a fraction of the time, because that guy has nothing to send. And furthermore, even when I'm not alone, I will tend to have an older packet than he does. So I might have priority over him. So when I do this, 90% of the time, I have here a better service rate than 50%. So I have a lot of regret. So this is, I don't know what the service rate will be, but 50-somewhat%. And here is still 47. But yet, I clear everything. Because in this system, the queues get cleared. So it's selfishly good for you. You have regret, but turns out you're wrong about this. This is perfectly good and better for you too. So what's happening here? What's happening here is our notation about no regret is broken. So this is what I wrote as a no regret condition, that the amount you get is bigger than utility with a single action with hindsight minus a little bit of an error. But this notation is broken. It forgot that there is carryover effect between iterations, because we wrote things like utility I at action AT. Utility actually depends on the previous iterations also. And this is what we're actually doing if I look at the algorithms what achieved the no-regret learning. This is what we actually did. First of all, I changed the notation. Utility of I doesn't only depend on time t, it depends on all the previous steps. This is all the steps 1 to t. And what do these algorithms do? And hopefully everyone with even minimal memory of learning will know what these algorithms do. It's called explore, exploit. Occasionally try out stuff and see how it works. This is what occasionally trying out stuff and seeing how it works. That is, the previous iteration stayed what it is, and occasionally tried X and see how it worked. But the history didn't change. Up to t-1, it's what it is. You just occasionally tried it. So what it meant is that you limited yourself to the instantaneous effect of switching, and not a possible longer-term effect of switching. And going back to the example here, the instantaneous effect is bad. 0.47 is bad. It's the long-term effect that's good for you. And I guess going back to the learning, you might think that what we really want is something like this. You have to be careful here, because this is not an achievable condition. But what I want to know, what would have happened if other people stay with this strategy, but I would have consistently done X all the time? This is not what explore, exploit is trying. And this is not a condition we are reaching. Turns out this condition as written is too hard. It's not doable, but similar things are achievable. So what's wrong is that if there's carryover effect, your strategy has a long-term consequence, and no-regret condition is explicitly ignoring that consequence. And that's what's presumably wrong with it. So, I guess, maybe again, the theorem we have is about an equilibrium condition. It's not about learning. I can even admit to you that here is the bad example. And that's where the E over E-1 is coming from. There are n queues, all same arrival rate, and n perfect servers, and these idiotic queues using balls and bins. They uniformly randomly choosing a server every iteration. This is a super symmetric solution, so obviously it's a Nash. What the heck could they do? They're all identical. And you know what's wrong, because they uniformly randomly choosing their bin. 1 over E fraction of the bins no one's using, and we're wasting the capacity. And that is what I'm losing. That's the E minus 1 over E. 1 over E fraction of the bins got wasted here because no one sent that packet there. this is not an equilibrium any learning algorithm will get to. This is a very unstable equilibrium, like a really weird one. So possibly if we had a learning algorithm or learning condition here, you could do even better things than this. This seems like a really weird bad example, yeah, or unstable bad example, yeah.
Is one of the reasons that no learning algorithm would end up there is that like there's sort of implicit or explicit, both implicit and explicit correlation that'll happen if everyone's learning?
Yeah, it's like if I had a dynamical system that describes your learning algorithm, this is an unstable solution of the dynamical system. So the systems don't converge to unstable points, unstable points. That's my argument of why. But again, I don't have a dynamical system, so this is all hopeful thinking. Yeah.
Maybe explain this, but what does it mean for queues to choose servers patiently?
I didn't explain it. So that theorem up there is an equilibrium theorem, which says that, and actually I'm sorry I hid those slides due to lack of time correctly estimating it, but here is the actual statement. Maybe best to think back of that 2Q example. If they were choosing a strategy of how they randomize between the servers, like 90% here, 10% here, or these guys like uniformly random, then I can define a game of what happens with that strategy, like how badly your queues will build up, or how long does it serve for your expectation, how long it gets you to serve a packet, and that's your objective function. And you're choosing a distribution that optimizes that objective function. That game has a Nash equilibrium, which one has to prove, but it does. And that Nash equilibrium has this property. Why do I call it patient? Because instead of instantaneously looking at the effect of this distribution, you look at the long-term effect. What's the expected service rate if you're using the distribution you're using? Does that make sense? So maybe paging back to the example, like in this particular service rate, the queue buildup is nothing. They serve everything, and they have some amount of time, like in expectation in something like 2 or less than 2 iterations, everything gets served. If they do this distribution. If they fully go up there, then it's an increasing function of how long it gets to serve. So this distribution is better than that one. Does that make sense? So they're looking at the distribution and looking at its long-term effect rather than the instantaneous service rate, which is why I call it patient. OK, that's the worst case. The proof ID, I guess the only thing I'm going to say about it, it's an equilibrium analysis of the classical equilibrium analysis type. Like look at an equilibrium, and then we try to think of deforming the equilibrium and claiming that this symmetric solution is the worst. Like if it's not symmetric, then you can massage it to become symmetric and only gets worse or better or whatever. The worst case is the symmetric solution. So I guess maybe we'll end up with a couple general thoughts on what I think my future thoughts in life is. No-regret is certainly beautiful and easy to use and nice. It's on the pro side, it's a simple behavior assumption. Again, we have some fair amount of evidence that repeated learning setups, both systems and humans actually achieve this condition, or mostly achieve this condition. It does seem to imply reasonable social outcomes, but there is something wrong in this carryover effect, that it's not taking into account that long-term something else might happen than the short-term because of this. One has to be careful here, and I guess there are beautiful other papers that also say what's wrong with no-regret learning. I'm not the only one who ever noticed it. I guess maybe highlighting is this Braverman and company paper that won a Best Paper Award in EC 18, where it says that in an auction it's dumb to run it, that if you're a no-regret learner, the auctioneer can take advantage of you. What I like asking is, would love to have another condition that's like no-regret learning, but takes account this condition, that is doable, that it's observed in data, have all these properties up there, but be a little bit better. I did show you that even with carryover effect, learning does do something reasonable, but that can be too simplistic and can be too myopic. I guess when I first gave these talks, I actually had a conjecture of what is the better condition, and that was, for those of you in the know, is policy regret. Maybe some of you, it turns out policy regret is not the right condition. These friendly people have a paper in the previous NeurIPS or Wambach NeurIPS proving that policy regret is not the right condition. It is an artificial example, again, unstable, crazy, definitely no algorithm can reach it, but it does satisfy the policy regret condition, and it still needs a factor of 2. So I think something similar might work. Their proposed solution is that their players have to coordinate if they want something better. I guess I'm not proposing that. I think we should just have a better condition. And I guess I want to end with what I said, that I also don't believe. I believe that this particular equilibrium is really crazy, so natural learning things don't converge to this craziness. So maybe one can do better things here because this is unstable. OK, I'm going to stop here, and thank you, everyone, for all the attention. And hopefully, for various parts of the audience, you still had some take-home message, but thank you for your patience. Yeah.
So in this example, I guess another kind of natural strategy is for the first queue to only send packets to the first server, the second of the server, the second, and it's also in equilibrium, right? So why? And then there's no need for slack there. So why are we analyzing the worst equilibrium if there is a kind of like a better one? Like, how do we choose which Nash equilibrium?
It's a good question. There are multiple questions here. You could ask the price of energy has a matching concept called price of stability, which instead say choose the best equilibrium and analyze that. That's your best hope, that hopefully they find this good equilibrium. You can ask yourself, OK, but how did they know to find it? Who helped them coordinate on the right equilibrium? So there is the middle thing, which I'm more fan of, and there are some old papers that try to do this in the classical learning setting, is learning outcomes. That is, you have a dynamical system as they're learning, and only the stable solution, unstable solution don't count. Can you say better things if you only count stable solution? That is, things that such a dynamical system can converge to. And a worst case among those, but not counting these unstable things. That's a middle question between the two. You can also ask questions that I don't have even an example of anyone proving anything. The likely outcomes, like that if you start from a random start with high probability, you convert something decently good. I don't have examples, but that would be really nice. So there is a selection of which equilibria, which solutions are reasonable here. Good question. Of course, if you prove something in the worst case, then you can be pretty certain that it's OK because you took the worst case. But I don't have a better answer than this. Yeah.
One quick question. The example for low policy regret not being good should be different from the one you showed, right? That one gets fixed with policy regret.
That example got fixed with policy regret, yes.
So they came up with other examples.
Yeah, they have other examples. But I don't know how much you've seen these sort of bad examples with no regret. It's a very artificial sequence, not even as natural as this one. It's not an equilibrium. It's a sequence of actions that happens to satisfy the no policy regret condition. Yet it needs a factor of 2 blow up. It's obviously not an outcome of any learning action. It's a long sequence of actions And the method seems to be that you just take this and repeat it. It's a coordinated set of actions. There's a set of some T things, and they have to keep repeating it every iteration. And it satisfies the condition, which is a classical thing people do with proving that no regret is not good for something. That's what they usually do also. Like, there are a lot of these in the no regret literature. So it is artificial, but it does prove that the condition itself is not good enough. So for example, I would still want to conjecture that if I take the policy regret algorithms, those will be good. So the condition is not good, but if I take the classical algorithms that the original policy regret papers propose, that here is an algorithm that achieves policy regret, those algorithms will do it, I think. Not that I can prove it, but that's my conjecture. That the algorithm will be, if everyone does an algorithm like that, that will be fine. So what does the algorithms do? Literally what I think one should do, instead of explore, exploit, explore once and then back off, please explore longer. You want to see the long-term effect. That's what the policy regret algorithms do. I still believe that those work. That the example is not vetoing that.
And is it even like explore like the same action for a while?
So there is that problem that there isn't, the optimal here is not a single action. So you need to do something like convex optimization, because the optimal, as you see in the example, is some percentages come down to the 47. If you fully come down there, it's bad. If you fully up there, it's also bad. But if you mix between the two, it's good. So there is a semi-convex, somewhat convex, not quite convex optimization that you should try things with. Yeah, good point. So it's not a finite problem, right? Because the solution you're looking for is a mix. Thank you, everyone. Thanks for showing up. Very appreciated.